Today we're going to talk about sets and set notation. So there are many sets of numbers, and sets of numbers could be, this word is finite. Does anybody know what that word means, finite? It's actually the opposite of infinite. So what does infinite mean? Yeah, and infinite means that it's never ending, right? You could say the universe is infinite. That's so weird. It blows my mind. But finite would be an actual countable amount. So when you have a finite amount of money, you can actually count it out, right? And there are ways to express our sets. So we have a roster method we're going to go over, set builder notation, interval notation, and lastly, a number line. We've actually looked at number lines when we were solving inequalities. You have 4 spots here, and I ran out of room because I write too big. But before we start delving into these, I just want to talk about our real number system. So the real numbers, we can break them into sets. And the very smallest set, which is actually still an infinite set, is the counting numbers. And another word for counting numbers, another name for them, would be the natural numbers. So these are the numbers that occur in nature, and we use them to count with. So if I was going to count up my class, what number would I start with? 1, 2, 3, 4, 5, 6. Exactly. So counting numbers, and I'm using these braces, 1, 2, 3, ... Does anybody know what that ... the 3 dots, what's it called? Ellipsis. Yes, I have a problem pronouncing that word, ellipsis. An ellipsis means that this number, whatever pattern we've established here, is going to keep going. So these are what we call the counting numbers, okay? Containing within the outside of the counting numbers, but counting numbers are included, another set of numbers is called the whole numbers. The whole numbers contain all of the counting numbers, and they also contain 0. So 0, 1, 2, 3, ... These are the whole numbers. And actually, I just listed the counting numbers again, and the way I remember that 0 is actually not a natural number, right? 0 is very unnatural because what is 0? Where is 0? I don't see 0 anywhere. And it took humankind a long time to actually establish the idea of 0. There's a biography written, 0, the biography of a dangerous idea. Okay, so if you say 0 is a whole lot of nothing, that could be a way to remember that 0 is a whole number, and then you include all of the counting numbers are also whole. After this set is called the integers. And the integers include the negatives and all the whole numbers. So you have 0, 1, 2, 3, ellipsis. Am I saying that right? Ellipsis. And then you could go backwards, -1, -2, -3, and ... in the other direction. Sorry, I'm trying to get my set braces in there correctly. They're really hard to draw. So our integers are basically the numbers you usually see on the number line. But there are more numbers that are on the number line. You just don't always write them out. So after integers, all of these numbers are contained in the bigger set. All of these sets are infinite, though, called rational numbers. And a rational number would include all fractions, a divided by b. So if you have a and b are fractions, if you divide these, a and b could be integers, okay? And if you divide them, you get rational numbers. But b cannot equal what number? What number can you not ever divide by? Yes, you can't divide by 0. Okay, so we would say if you had a number, let's say you had the number 6 and you divided it by 0, we would call that undefined. Could you have 0 divided by 6? What is 0 divided by 6? is 6. No, it's 0. Think about it in terms of money for a minute. Imagine you had $0 and you were going to divide it evenly among you and your 5 friends. 6 people were going to divide up $0. How much money would each person get? They would get $0, right? If you had $6 and you divided it among 0 people, how much would each person get? Well, that question doesn't even really make sense. So we wouldn't really, that's why we call this undefined, all right? We have other kinds of rational numbers. We have proper fractions, 1/2, also known as 0.5. We call this a terminating decimal. 1/3 would be another example of a rational number. It's not whole, it's not counting, it's not an integer. 1/3 is 0.3 repeating. We call that a repeating decimal. And I ran out of room there. Okay, so we have rational numbers. All of these are rational numbers. How come a counting number can be counted as a rational number? Well, what is 4 divided by 2? 2. And we said that 2 is a counting number. 2 is also a whole number. 2 is also an integer. And 2 is a rational number. So any number inside here can be made into a ratio, which is why all of these numbers are rational numbers, whereas a proper fraction wouldn't be considered a counting number because you don't count 1/2, 2 halves, you don't count like that. The opposite of a rational number is this wacky little group over here, which we call, any ideas what it's going to be called? Irrational. An irrational number, the most famous irrational number, does anybody know what it is? It's actually 0 is a whole number, right? It would be pi, which is approximately 3.141592654, rounded off, right? And ellipsis, it goes on for infinity. When we have a repeating decimal, we can use what's called bar notation. We put the bar over the number that's repeating. But the problem with pi is these digits are, of course, going to repeat, but they're not going to repeat in a specific pattern. There's not going to be a pattern to the repetition. So it's not entirely random, but I can't put a bar over any because I'm not going to get that same repeating pattern every single time. Another example of an irrational number would be like the square root of any non-perfect square. Square root of 2, and if you do the square root of 2 on your calculator, second square root 2, you would get approximately 1.142, or 14, no, I said it wrong, 1.4142, and again, I have to use a ... ellipses at the end because there is not going to be a pattern of repetition to that decimal as well. And then finally, another one that's going to come up when you get into your higher level math classes, I might as well point out, is this number e. So if I go second ln, I'm going to go e to the first power. E is approximately 2.71828, and again, ... because that number is going to be going on for infinity. You use it a lot for exponential growth, and you're going to use it a lot in calculus classes. But these are just 3 different examples. If I had the square root of a perfect square, what's the square root of 25? In other words, what number times itself is 25? 5. So the square root of 25 is actually a counting number because the square root of 25 is equal to 5. So when you take the square root of any perfect square, you get a counting number. And then all together, the rationals and irrationals are in one set called the real numbers. Okay, now is the time when I like to tell the math joke, one of the more famous math jokes, okay? You have this number I, which happens to be the square root of -1, and it's hanging out with its friend pi, and I says to pi, do you know what I says to pi? Be rational. And then pi says back to I, get real. Okay? Because I is not a real number. I is what we call an imaginary number. And we'll get more into that in our more advanced math classes as well. But I just thought I'd point that out so that when you see the joke, you'll know what they're meaning, what they're talking about.